For over 2 decades, we've partnered with the world's leading processor makers to solve the toughest thermal challenges. From the largest AI clusters to the top supercomputers, Cool IT cold plates set the standard for liquid cooling, combining unmatched reliability and performance. See them in action at OCP Global 2025 and learn more at coolitsystems.com.
Especially this year, we're seeing the real leaders in HPC, the real leaders in AI systems and hardware. Almost every single one of them has been putting stakes in the ground and saying, okay, we're going to do this now. There's a really good example of photonics in the scale-up, which is the Huawei system. Early predictions, I would say we're talking about at least 2 orders of magnitude in performance.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hi, everyone. Welcome to the At HPC podcast. I'm Doug Black of Inside HPC, and with me is my co-host Shaheen Khan of OrionX.net. And we're very happy to have with us today a special guest, Keren Bergman, a noted expert in the field of optical I/O interconnect technology. Keren is the Charles Batchelor Professor of Electrical Engineering at Columbia, where she also serves as the faculty director of the Columbia Nano Initiative. She also is a co-founder, starting 3 years ago, of Escape Photonics, which is in the optical I/O arena. And she appears regularly at technology events, including the Supercomputing Conference, to discuss optical I/O. So, Keren, welcome back.
Thank you so much. It was a great fun to have the previous chat, and I'm really looking forward to today.
Great.
Such a pleasure to have you, Keren. Our last episode was one of our more popular episodes. I know there's a lot of interest in the market and great time for us to catch up. We were all reminded that it was 2.5 years ago, just like that. So
it's amazing how quickly things move forward. Even 2.5 years ago, a lot has accelerated since then.
Yeah, you came on with us in April of 2023, which generated a lot of interest. And there's a lot of ongoing interest in optical I/O as a potentially new foundational technology that will allow HPC AI class servers to run faster and cooler. So why don't we just start with a very big picture perspective, Keren? What's changed with the technology over the past 2+ years?
I would say, the most dominant changes have been really the maturation of the ecosystem. So just 2.5 years ago, obviously, already a lot of interest in this technology, with silicon photonics primarily being the forefront technology for photonic interconnects, and the possibility of using them in the context of AI data center systems, HPC systems. As opposed to optics, of course, has been used for decades in long-haul fiber optic communications, and even in data centers, in the longer reach connections. So this is not what we're talking about here. This is really getting photonics in the data path, in what I like to call the data path. So over the last couple of years, there's been continuing, I would say, explosion of both, small and large companies that have made strategic and really put stakes in the ground for bringing these to the commercial world. The most, I would say, in my view, the most pronounced announcement came from NVIDIA back in March of this year, that they were essentially made the announcement that they are going to be using co-packaged optics in their systems, initially to their switches.
Okay. And just to clarify exactly what we're talking about, I sort of needed this clarification. We're not talking about moving data within the chip, but it's chip to chip within the server, within motherboards, etc. Is that correct?
Exactly. Within the chip, over very small distances, let's say sort of less than a millimeter or millimeters, copper is fantastic. Copper can do very high density. Copper can also deliver very high bandwidth density, Copper can also deliver very low energy consumption per bit in the single to tens of femtojoules per bit. And it's cost effective. It can be used in 3D integration, and there's a huge manufacturing ecosystem around that. So really, when we talk about co-packaged optics, or sometimes I refer to it as embedded photonics, it's really about bringing the photonic interface to the chip and then using the advantages of the optical domain, which basically are you can send a lot of data over any distance you want. Whereas in electronics, of course, the longer the distance over which we send data, we experience a lot of loss, and we have to amplify the signal and spend more energy as a function of the frequency. In the optical domain, the very simple fact is that the losses of the optical medium, whether it's an optical waveguide or whether it's a fiber optic cable, are extremely low. And so it's the same signal whether we send it over a few centimeters, a few meters, or maybe even up to a few hundreds of meters across the entire HPC system, across the entire data center. So that's really one of the key advantages. And so when we're talking about bringing data movement in the optical domain to these HPC AI systems, the technology that we're referring to is the interface. Let's put the photonic transceivers somewhere on the chip, whether it's at in the form of a photonic I/O chiplet or some other co-packaged designs, formulations. All those things are obviously up for discussions, and there will be different photonics in different places in the system as well. But that's essentially what we're talking about. It's transitioning to the optical domain at that distance point. And so you imagine having photonics, within the blade, within the rack, and also, of course, as we already have today, between racks and across the system.
And Keren, just quickly, I think the first thing on everyone's mind listening to our discussion is, this notion that optical I/O is potentially such an exciting technology, but it seems to have a receding horizon. We're always 2 or 3 years away. What's your take, and we can get into the particulars, but what's your take on the commercial readiness for this technology?
It's a great question. And you're right. I've been obviously, working in this field for decades, and we are always excited when we do research, and we like to think about the insertion of those technologies in commercial systems. And you're correct that in the past, you could say it was the technology of the future and always will be. But this is different. This is really different. And, being still cautious, there are a few reasons that photonics hasn't seen the full blown, implementation. The number one is cost, as it always is, right? Cost is number one. And, for example, in the latest NVIDIA system, the Blackwell, still it's made out of copper, right? The interconnects are still copper. And that primarily the reason is cost, not performance. Photonics, it's already known that photonics can outperform the equivalent electrical interconnects, both in the bandwidth density and in offering lower energy consumption. But, for various market reasons, it's the cost. So why is the cost? The cost is also obviously a factor of the ecosystem, the commercialization, the manufacturing ecosystem. And that's, if I go back to the first comment I made, what's been changing in the last, 2.5 years or so since our last conversation, it's really the further maturation of this manufacturing ecosystem. Are we all the way there yet? Of course not. But because what we're seeing, and especially this year, we're seeing the real leaders in HPC, the real leaders in AI systems and hardware. Almost every single one of them has been putting stakes in the ground and saying, okay, we're going to do this now. And that means that they have the suppliers, the fabrication, the manufacturing, the packaging, with real funding, with real orders, with real markets behind that. So I can almost anticipate the next question is like, okay, when, right? When do you think we'll see it? And I would say that at this point, we're really looking at 2028 as being the year. That's a little bit my opinion, and obviously various talks and conversations and the status of putting together everything that I know of what's out there. I think this is about 2028 or so will be the first real deployment of co-packaged photonics in systems. We can come back in 3 years and check on that. I'm hoping that it will happen even sooner. And of course, we'll start to see some things sooner. But I think that will, in my opinion, I think that will be when we can actually say, look, here it is.
Keren, has the science been settled for the products that are being developed, or are they still being pursued in various capacities? Is there like one direction that the industry and the manufacturing world is pursuing, or are new ideas coming in from various directions?
There's always new ideas, of course, but I would say that they are really about the next generations. In terms of how things will be done, there's still quite a bit, there are multiple approaches that are out there, and they will have to be shaken out in the marketplace with vendors. And, there's, of course, lots of questions about scalability, reliability, all the usual stuff that needs to be proven out for mass scale manufacturing and adoption. So those debates are very much ongoing. There's, various technologies that are being quote unquote baked off at this point. But I think that if you step away and look at the picture, definitely we're going to be using some form of wavelength division multiplexing. How many channels is probably going to be a small number of channels initially, and then a growing number of channels as we continue to scale into the future. The co-package, the assembly of the photonics together with whether it's the compute or the switch or the memory, those approaches of exactly how things are going to be packaged, assembled, there are a multitude of technologies and approaches that are being pursued right now by various players, and we will see. Maybe several of them will succeed, because it's not a one thing. I just want to make that clear. Co-packaged photonics and systems is not a one thing. There will be photonics that is co-packaged perhaps with the switch, inside of the interconnect network. There will be other photonics that's used potentially for longer distances in the architecture, and so forth. So I expect that there will be different solutions for different points in the data center for sure, and within the system as well.
What is your perspective on the software protocols that run on these interconnects? And is that any different because the fundamental technology is different?
It will have to be the same. I think for a technology to succeed, there's already a pretty tall barrier to entry for photonics, as we discussed earlier, for the cost, right? If on top of that, I ask the system providers to revamp their software, I think that puts us, many steps backwards. I don't think that will be a successful path. Mm-hmm. Maybe sometime in the future, but at this point, it's really about inserting this technology in the most seamless way possible. One of the big debates around co-packaged, co-integrated, or photonics is the replaceability. Today in the systems we have, of course, the well-known pluggable photonics, right? Very easy, very useful. Vendor interoperability, everybody can design to it. Something breaks, you replace it, right? It's a simple pluggable, as it's called. And many applications, of course, longer reach, shorter reach, all of the above. And those things are not going to go away. They're going to be part of the future systems as well. But now we're talking about putting optics more inside the real data path of the applications, and really gaining the benefits of the integration from the point of view of the bandwidth density. The pluggables don't even come close to the bandwidth density that we get from co-packaged optics. It's like maybe 2 orders of magnitude difference. That's how big it is. And of course, the low energy consumption of the co-integrated optics. But it's co-packaged, co-integrated. So it's a module. So if some part of it breaks, the laser breaks or this fails, then what do we do? Do we need to replace the whole module? What's the strategy? So those are some of the questions. I think they're all solvable, 100% solvable issues. But those are really where the technology questions are. The software is, if someone has an approach that requires a redo of the software stack, it will not succeed in the near term for sure.
Well, my motivation to ask was what we saw with rotating disks and solid state disks. And initially it was all like slide in and you can't tell the difference. But then once it got gelled, people said, but this is not rotating. This has different wear and tear attributes. I can optimize it this way or that way. And then that over time sort of permeated through the software stack because the awareness that the medium was different had an impact. So for something like an interconnect, I'm not sure the same analogy holds, but that was anyway the motivation. Is there any difference that might provide opportunities for optimization that will prove irresistible at some point?
100%, absolutely. And that will come so the first step is about the interconnects. So for example, putting a photonic IO on the socket that might include, GPUs, memory, and so forth, or as NVIDIA announced, a photonic IO on the switch module. But the next step, and this is still more in the research domain, is to also include photonic switching in the system. Now, I'm not talking about, of course, Google, for example, has optical circuit switches in their systems as a way of doing some for reliability as well as topology engineering, things like that, more at kind of the macro level. But I'm talking about photonic switches that would be, again, more in the data path and could imagine that we have this very large HPC AI system, with, 10,000, even 100,000 endpoints. If we keep the data in the optical domain, we can use optical switches to reach much further, sort of increase the diameter of the compute that's available to us. We actually have a paper on this at SC this year, so I'm very excited about that, using optical switches in these systems. When we get more mature with the interconnects and we're starting to look at photonic switches as well, absolutely, we will need to think about the full hardware-software stack. And that's a subject of research that I'm doing right now, as well as, of course, other people are pursuing. But it will certainly come to commercial at some point in the future.
So, Keren, I was really impressed by your statement that you said right now it's not performance, it's price. And I assume part of that means manufacturing price, production at scale. These are issues that really need to be ironed out. But are you saying, for example, NVIDIA's next GPU could use this technology as things stand now?
Yes, absolutely. Absolutely. I mean, where exactly where you put the optical interface is a design question. For example, the NVIDIA larger GPU, I guess it's the B200, maybe they're coming up with a new one, of course. The connectivity, inside of that, I believe is still going to be electronic because it's very advantageous to have it electronic. But at the socket level, where you have the GPUs and the HBMs typically, to include an optical I/O, photonic I/O, what that will enable you to do is really scale out that. So as we know in these data center systems, right, we talk about scale out and scale up. So scale out is when you string together, these thousands or tens of thousands of servers. But scale up is really in, your compute, your closely coupled, interconnected, high performance compute. And so, for example, we go back to the NVIDIA system because obviously, they're the dominant in the market. So like the NVL72, right? That's a scale up. That's an example of what I would consider a scale up. And it's all copper at this point. If you went to photonics, you take even the same GPUs and you go to photonics, it's mind-boggling. I mean, we're talking, first of all, you can expand the domain. You're not limited to 72. You can imagine potentially thousands. And with equivalent or better, much better bandwidth densities at the same, very importantly, it's about keeping the power envelope from growing. That's one of the key limitations today to computing. It's about power and energy consumption. There's a really good example of photonics in the scale-up, which is the Huawei system. If you're familiar with it, they use inferior GPUs in their systems because of various export controls and things like that. So the GPUs that they use in their system, at least in the one that was published, has GPUs that are about 3 times less performance than the NVIDIA GPUs. But they just took conventional, not this most advanced photonics that I'm talking about with bandwidth densities and all that performance, but they just took conventional photonics like linear pluggable optics and connected the system in the scale-up domain. And we're able to create a system that's approximately twice as powerful, computingly powerful, as the NVIDIA NVL72. So they start with 3x less performance compute, right? Compute processor. But just using photonics, it just expands the physical domain of your compute capability because you just can connect more compute to it. You're not worried about, the losses and the distances and all of that. So just imagine what you could do if you take the most advanced GPUs that are available in the world and combine them with this new generation of embedded photonics, co-packaged photonics. Early predictions, I would say we're talking about at least 2 orders of magnitude in performance. That's the reason that we're so excited about this.
For more than 2 decades, Cool IT has partnered with the world's leading processor manufacturers to solve the thermal challenges of the most powerful chips on the planet. Our cold plates deliver the highest reliability and performance, enabling hyperscale and neocloud clusters to run the most demanding AI workloads. We design and manufacture liquid cooling products at scale that power the world's top supercomputers and AI infrastructure. See Cool IT technology in action at OCP Global 2025 and learn more at coolitsystems.com.
Are you saying, well, it makes sense, I think, that if you improve the interconnect efficiency, bandwidth, latency, coherency, that it allows you to use lesser GPUs, but more of them to get to the same place because the efficiency doesn't drop as fast, et cetera, et cetera? Is there such a thread there?
It allows you to use as many GPUs as you want, whatever you have, but much, much more efficiently, and also to be able to scale up the numbers that if you want to use, right? So sort of the typical architecture today, due to bandwidth limitations, is hierarchical, right? If I look inside the socket, what I mean by the socket is this typical package that we have with the compute, GPUs, HBMs, etc. Inside there, the bandwidths are fantastic, on the order of 10 terabytes communication bandwidth, all electronic. As soon as I get outside of that socket and I can connect some of these together via switch fabric, electronic switch fabric, the bandwidth takes about a 10x drop. I go one more and I build out a system. So for the scale out, and I take another 10x hit. So what the photonics will do is bring it into that 10 terabyte, right? Start there. And now I can go anywhere I want and still have that incredibly high bandwidth that I today have only inside the socket.
So it is eliminating distance, essentially.
That's right. It's essentially creates a system that we can say is distance independent. Of course, very important, we still have time of flight. We have
latency.
We have to deal with the speed of light. We can't get rid of that. There's going to be some limitations on how far we can scale things, but for AI systems, the sensitivity to this latency is not as severe.
Mm-hmm.
And so the potential gains for these systems in performance are just incredible. And especially, now that the new measure is going to be, forget about flops or anything like that. It's going to be in units of power.
You mentioned femtos per bit.
Even I saw a recent article where OpenAI, right? They just have some contracts with AMD and NVIDIA and et cetera. And the contracts are in gigawatts.
That's right.
Right? So this is the number that matters now. And so what optics will do is imagine that we can give you 100x performance inside of that same gigawatt.
Right. So this is a good segue into a question I had about materials. What is the state of science, research, production when it comes to novel materials that are optimized for speed, energy loss, etc.? Or is it all the same because it's all fiber optics?
There's been a lot of advances and a lot still more need to be done, for sure. We can always, on the material side. So the big thing, right, the kind of the dominant thing has been the advent of silicon photonics. So now we can basically have we can design, we can fabricate fairly complex photonic circuits, photonic integrated circuits, PICs as we call them, in conventional CMOS fabrication. So my lab, as well as many others, we fabricate in 300 millimeter foundries. There are specific runs, optimized for photonics, but they're using conventional tools that are used in CMOS fabrication. And there are several commercial ones, Tower Jazz, Global Foundries, and now TSMC, of course.
Mm-hmm.
So that's the main thing. Now, the bad news is that, okay, so, we can't talk about photonics without talking about lasers. Sometimes people forget that you need the laser.
Yes.
Photonics is great, but we need the photons to make it work. And so with all these wonderful things that we can do in silicon, unfortunately, silicon is not a great material for lasers. It's an indirect band gap, of course, and we cannot, at least right now, we cannot make lasers in silicon. So the silicons are 3-5 typically, materials that are used. And so they somehow need to be, that's why the packaging problem in photonics is and continues to be a big issue. How do you bring the laser in? How do you integrate the laser? I mentioned that we are definitely will need to go to wavelength division multiplexing to get to these kinds of bandwidth densities that we're talking about. How do you bring in multiple colors of light into the chip? I can quickly mention that the company of which I'm a co-founder, Escape Photonics, one of our key novel technologies is that we're able to make things called comb lasers, where using a single laser, we're able to generate many colors all at the same time. So that's one of our key technologies. But in general, the issue of the laser is a major issue for getting this technology into the systems. And that, of course, translates into how do you combine? Do you have the 3-5 material outside of the silicon? Do you combine it with the silicon in some kind of a packaging platform? There are other companies and researchers that are working on growing 3-5 on top of silicon and other techniques. So that's a big one. That's a big topic and big issue. Of course, there are other materials as well. For example, one of the issues that we're working on in research is how to make the photonic circuit less sensitive or even completely athermal, and not sensitive at all to thermal variations. Any photonics is naturally sensitive to temperature, because if you change the temperature, one way or the other, the index of refraction of the material is going to change, and therefore your photonic circuit is going to change in some way, especially when you're doing dense wavelength division multiplexing and using things like resonators, then it changes pretty dramatically. And so how do you navigate that? And are there materials that are less sensitive to temperature? Are there materials that can compensate for that? So again, that opens up the future of research is bright because there's many important problems to solve.
There's still things we don't know, you're saying.
Absolutely.
This all it just echoes of what's going on in quantum, only I'd say less so, in the sense that you're closer than quantum for readiness. But is there going to be an issue? Say we're 3 years out, these new chips are bursting on the scene, everybody wants to use them with silicon photonics. What about integration of the new chips with the installed base of copper interconnect-based chips? Is that going to be an issue in data centers or in servers?
You mean that there'll be like a mix of some things with just copper and some things with just photonics? Is that your question?
Yeah.
It's a good question. My thinking, definitely a good question. I don't know that, I don't have a clear answer, because I would say, the system owner, right, the system vendor or the operator that has maybe the more mature technology in their data center and now wants to add photonics, I don't know that they're going to keep the old stuff and add, somehow add the new stuff as well. More the things that I hear and work on are replacement. So, we're going to, replace the racks with basically, photonic enabled racks. I don't know about the, operability with, older stuff with the neurophotonics? It's a fair question. It's definitely a fair question. Yeah.
That's the unit anyway in the data center these days, especially with the way NVIDIA has been architecting them.
Yeah, I mean, definitely the data centers have fiber. The fiber installation is an expensive thing, and they do love to upgrade, without having to rip out the fiber and change. And I think that's very doable. That's not going to be an issue so much as inside the rack. Plus, everybody wants to sell new systems, so that's good for business.
That's right. I had a question about also manufacturing. One of the things that keeps coming up with anything that is analog or analog looking is that it is hard to consistently manufacture the same specification because it's the AM radio that you have to tune, or like a piano that falls out of tune. Is that an issue with optical interconnects, or are systems sufficiently consistent or can be manufactured, or are AI enabled to tune themselves back to the right zone? What does that situation look like?
Yeah, so in the context, right, of these photonic interconnects, that issue does exist, but a little bit different, perhaps, than what you had in mind with regards to analog systems. So a typical WDM photonic link that we are envisioning would have data modulators and receivers, right, that are designed to operate at a certain wavelength. And we can combine them together so that we can have many wavelengths potentially, running through the link. That's how we get the bandwidth density. We scale in the number of wavelengths. And definitely when we manufacture these modulators and filters and other components in CMOS fabrication, in sort of conventional foundries, and they come out, there'll be some variations, right? We design them for, this exact frequency, but we measure and the resonance is a little bit off that frequency. And that modulator needs to be tuned. And so that's absolutely being worked on. That's really part of the package right now. Mm-hmm. So the circuitry that goes along with interfacing to these optical chips typically has two parts. It has the high-speed digital data part, right? The data transmitter and the receiver side of it as well. And it also has a bit of an analog circuitry, control circuitry, that is part of the chip, part of the system. It could be a separate chip sometimes, depends. But that is used for calibrating, tuning up, getting the photonic chip lined up to where it needs to be. So that's certainly is an issue. And all of these things can also change with temperature. So these control and has to adjust for that as well. But, it's something that we're used to doing. We've had lasers, commercial lasers for many decades. All the lasers have, circuitry that keeps them, in tune and so forth. We've had transmitters for fiber optic systems, for decades. And so we know how to do it. The challenge for this application, for inside the AI system and the data center, is to be able to do it in much smaller footprint, right? To regain that bandwidth density and with a lot less energy. Its energy is like the first, second, third class citizens in all the designs. Very important. So right. Definitely technical. Again, not insurmountable challenges, but absolutely part of the process.
Keren, on power consumption, what is your sense of how things will play out? When these chips come on the market, will data centers run up demand for compute power up to the same level of power consumption that data centers are already consuming now, or more so in the future, so that it nets out that we haven't really addressed the power problem? Or will this make a big dent into the power consumption challenge?
I think that, if you have a data center that you built, with whatever hundreds of megawatts, you're going to try to use all the power that you're paying for. You're not going to all of a sudden use half the power of whatever you built. What the photonics will do is enable you to continue to scale your compute and capabilities inside of that envelope. And so I believe the way that it might roll out is the initial photonics will not be the most energy efficient that we can make things. There's still more research that we can do. There's still more technologies that we can bring to the table, make things even more efficient than they will be in my magic year of 2028. And that will be one, let's say, mark in the ground, right? Let's imagine that we bring in this first generation of co-packaged photonics, and you're going to get definitely a gain in the compute. You're going to get a gain in the efficiency of how you run the application. So you can run the application. Imagine you have a certain application, instead of running it a certain amount of time, now it takes 10x less, right? So you can run 10x more things under the same power supply envelope. And as we continue to get better with the photonics, and we have paths towards that. Right now, there may be more in the research, but they are evolving, and the photonics will get even more energy efficient, and you'll be able to do more. Yes, I'm sure that, assuming that this AI generation continues to grow as we expect, more data centers will be built and more power will be drawn. But what we can do is make things a lot more efficient and maybe bend the curve. I wouldn't say we're not going to turn down the power, because I don't think the operators are going to turn it down, but we can bend the curve and make it scale much more reasonably.
Right.
Okay.
What does the global scene look like when you look at research as well as production? We mentioned Huawei, their Matrix, Cloud Matrix, I think it's called, or Atlas, and their Ascent. We've covered them in our podcast in the past. But obviously, the research on the global scene is also an interesting topic. Who's good at this stuff besides obviously the US and your own lab in the US?
Yeah, the US is very good. We have leadership in various things. I would say, China is amazing. They have put just incredible resources into this by basically doing what I hope we can do more of here in the US, is by having combined, very targeted efforts, from the government, industry, and research, the research enterprise, including universities and other research institutions, and just pouring resources into this. Are they ahead of us? I honestly don't know. But if I look at what's happening in China, I can see from the papers that are being submitted to conferences and publications, and at least what's in the public domain, amazing, really impressive. So they're a big player in this, and I believe they will continue to be a growing player. The US, of course, and obviously, of course, there's very strong work in Europe and in Japan as well, of course.
Right.
Is this sort of their strategy, really focus on the interconnect aspect as opposed to the pure processing part, to try to catch up with the West on chips?
It certainly is part, maybe because the processors part was more limited, due to the geopolitical things that are way over my head.
All of us.
Right? But one way or the other, it's highly accelerated. It's very impressive.
Last time we talked, I remember we also mentioned fabrication technology, and I seem to recall that you mentioned for optoelectronics, you don't really need the leading edge of chip manufacturing. And as you mentioned, like 300 nanometers would do. I don't really need 2 nanometers out there. Has that changed, or is that still the situation?
It's still 300 is a little high, but I would say, 90 nanometers and below. We use fabs that are 180. We use a fab that's 65 nanometers. So definitely much more mature technology than obviously the 2 nanometer or even smaller nodes. You don't need that. And the reason is, basic, because the optical wavelength is way bigger, right, than the electron. And so what we really need from the fab is to be able to make the optical photonic structures, the waveguides, the switches, the resonators, everything that we design smooth so that we don't have losses. One of the key design parameters is about minimizing loss. The less loss you have in the photonic circuit, the less energy you need from the laser, the less sensitivity you need from the receiver, and therefore the power consumption goes down and the more bandwidth you can send through. So loss, it's all about the loss budget as well, as a primary focus. So that's great. And you can achieve that with, processing technology nodes that are more mature. However, what's also very important, we touched on that a little bit before, is the variability. And if you use, let's say, a 65 nanometer node, right, but you use tools in that fab line that are advanced tools, that are used for more advanced nodes, then you get much more consistent accuracy and repeatability, and that can play a huge role in the ultimate performance of the pick.
I see. So it's almost like consistent quality of every data path, let's say.
Exactly.
Yeah.
It's also good for packaging, just to add to that a little bit. So, the photonic pick on its own, if I just give you a pick, there's nothing you can do with it.
Right.
You can't turn it on, you can't send any data, there's nothing you can do with it. It's like a brick of silicon. So I need to connect that pick A to a laser of some type or co-integrate the laser. And I need to connect everything to the electronic domain to send data, to power the laser, everything. And so the other really important aspect is the packaging. We talk about co-packaged optics, the package is the assembly and the packaging is very important. And the advanced tools, being able to do things, 300 millimeter wafer scale with advanced tools also lets you do things like 3D packaging that enables you to co-assemble with electronics in a very precise way. You can have very small pitches. You can all these things enable you to reach better and better bandwidth density and performance.
Right. And PIC you mentioned is photonics integrated circuit. That's what that means?
That's right. Right.
Also, I remember from our last conversation that photonics for communication, check. Photonics for computing, I don't know, complexity may or may not. What is your latest take on optical computing?
It's a very interesting topic. I think that at this point in time, it's in the research domain and very interesting. I myself am working on it. I think that there are some key functions that you can do in the optical domain that, because of the parallelism, the natural parallelism that you get in the optical domain, that could be extremely interesting and accelerating, certain compute functions. And my argument there goes, in the past, right, there's a long, sometimes colored history of optical computing, like back to the 90s, What some people did in the past was said, okay, I'm going to build a computer and make all optical gates and do everything in the optical domain. And that turned out to be, not a very promising path in the end and kind of crashed and burned.
Sounds really hard.
Yeah, so it was very hard. It was exciting to think about. I remember, we did things like optical logic gates and things like that. And it was nice research, but compared to what you can do in electronics, even back then, it's night and day. But let's say that we are getting to everything that we've talked about today, which is we've already paid the price of converting to the optical domain. Let's say we're in a world where embedded photonics, co-packaged optics is part of the system. Just like I said earlier about the switches, we can keep going. So now we already paid the biggest cost is moving from one domain to the other, from the electrical to the optical back. So we've already paid the price. We paid the energy costs, everything. Maybe we can do something with that data in the optical domain. Now it makes a lot more sense to me.
If it's already there, can we use it?
It's already there, yes. And so that's the question. It's still in the research domain, but I think that there are some really exciting things on the horizon. Yeah.
I was going to ask you about the cost of transceivers, and now they're embedded, they're everywhere. Are they wire speed and no issues on energy, or is that still like a lump that one needs to worry about? Sounds like is the latter.
The cost of the transceiver, you mean?
Just the cost in terms of time and energy, in terms of latency and energy.
Oh yeah, no, it's really minimal. It's really minimal.
I see.
Yeah, It's very minimal. It's almost instantaneous. It's like in the picoseconds domain. Yeah. So
got it.
Unless, let me just with a caveat. There are certainly transceivers where the data is much more complex, like a much higher order modulation formats, coherent modulation, all the stuff that's being used in telecom. No, those are not good for this application because you have to do a lot of signal processing and all kinds of stuff. So, which adds a lot of energy and latency. So that's not what we're talking about here. Here, when we think about these very stripped down, very typical to like HPC systems where you have a proprietary interconnect. Now it's in the optical domain. The latencies at the interfaces are really minimal.
Right. Excellent. A couple of years ago, I thought I had this brilliant idea that if you take a number and you want to factorize it, why, can there be like a prism and then you shine it and then whatever comes out on the other side are the factors? So then I go Google it, and indeed somebody had already worked on it.
Yes.
It wasn't a new idea. So it seems
It's
like
a
there
great
are...
idea. Yes, that and things doing like optical, that's what I meant by functions, like doing things like optical FFTs, other that naturally use the parallelism of the photonics.
Right. So I wanted to ask you about the company that you have co-founded. And I think for anybody who wants to go look it up, it's pronounced xscapephotonics.com, if I'm correct.
Yes.
What is it about? What are you guys trying to do? I was delighted to hear about it. And, as much info as you care to share with us.
Oh, absolutely. And thank you. Thank you for that. We're very excited. So I and two other Columbia faculty, Michal Lipson, who is the pioneer of silicon photonics, and Alex Gaeta, also a faculty at Columbia, also pioneer in nonlinear optics and especially comb laser technology. And our other founders at the company, CEO Vivek. So the company is about really bringing a lot of what we talked about to the commercial world. And the key differentiator that we have is the comb laser technology. So this is, imagine that you have a single laser that generates simultaneously any number of wavelength channels that are exactly precisely spaced. You can design and space those channels exactly what you want. Each one of the channels can deliver relatively high power, and it's all driven by a single laser which is a very energy efficient way to do it. If we sort of trace it all the way back to the wall plug efficiency and so forth. So this work started when the three of us at Columbia have been working together for over 15 years. And in the last number of years, we combined this comb laser, which generates many wavelengths together, with the link architecture work that I do to deliver everything that we just talked about, the high bandwidth densities. We're talking about, just to give some numbers, reachable to 10 terabit per second per millimeter to 40 or even more.
Wow.
As we keep going. And this is edge bandwidth density that you get out of the chip, fiber coupled. Inside, if you're thinking about a panel scale computing system, you can get even higher bandwidth density. It's just incredible. So we decided that this is very exciting. And a few years ago, we launched the company and are hoping to, obviously the vision of getting to these very large wavelength counts and bandwidth densities and so forth is on our roadmap. We have the ability to get there. And in the nearer term, the more where the market is going in the next, let's say 2-3 years, is a smaller number of channels. So let's say 8 channels or 16 channels. So that's primarily what we're focused on right now in the company, is bringing that to market.
Excellent. And the use case for this will be initially in data centers, inside racks, etc.?
Exactly. This is about the fabric, getting a photonic fabric, within the rack or blade to blade, those kinds of distances. Yeah.
I see. So really it just fills the spectrum of what is eligible to go optical.
Exactly right. Yeah.
Excellent. Well, good luck with that. I noticed the announcement from Columbia University, actually, because they were bragging about the funding that you raised, a very successful round. It was like $45 million or something. So that all sounds excellent. Best of luck for that. I think that's exciting and advances the state of the technology.
Thank you so much. Yeah, we're super excited about it. And as you said, there's a lot of interest in it. And we hope now is the hard part, right? Bringing this technology, doing all the engineering work and really bringing this technology to the foreground. And we're very excited about it.
Well, you have the dream team and
yes.
You've got the runway, so it all bodes well.
We hope so. Thank you.
Excellent. Well, thanks for extending this thing. Doug, any other topics from you?
No, I was just going to make the comment that, it's hard to raise that kind of money, but then it's harder to do what you're supposed to do with the money. So, but best of luck with all that.
Hardware. I like to say hardware is hard.
Hardware is hard, indeed. Yes.
Yeah. No, I think that's it. That was a great conversation, and really appreciate you bringing us up to speed in this area, Keren.
Thank you both so much. This is my favorite topic to talk about, so I can be here all day.
Awesome. Thank you so much. What a treat. Appreciate it, and look forward to catching up again later and running into you at SC.
Absolutely.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net.
Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen.
The At HPC podcast is a production of Orion X in association with Inside HPC.
Thank you for listening.